Continuing our study of local linear approximations, or using tangent lines to approximate functions, a very common application is to do limited time forecasting. For example, if we look at the population of Canada, which is around 33 million, and we find out that it's growing through immigration and childbirth at a rate of 300,000 people per year, well, that gives us enough information to generate some kind of prediction. In particular, if we call P of t our population, and we call P of 0, let's call that today, we say that's 33 million. The other statement that was given to us here is that P prime of t is 300,000 people per year. Again, notice the correlation between the units of P and P prime of t. If t is in years, P prime will be in people per year. The units of P and then the units of t divided by each other. All right. With that combination, we can very simply generate an approximation. So right now it's 33 million, so we can keep that, plus the rate of change, 300,000, times here, we'll add our extra ingredient here, t minus 0. And that's our, what we called a value before, that goes here. This would be our f prime of a from our earlier formula. Let me make that look like quotation marks. Let's leave it as a. And here is f of a. So the amount in the future, or past, but future in this case, would be f of a plus f prime of a times, remember the form we saw earlier was x minus a, now it's a t. T is our independent variable, so t minus 0. And what this model lets us do is capture the idea that every year, every time t goes up by 1, we're going to add 300,000 people. And so we can do things like estimate the population 2 years from now. P of 2 is going to be approximately 33 million plus 300,000 people per year times how many years? Times 2 years. So 33,600,000. Now, it's not going to be exact because, of course, the rate next year might not be exactly 300,000. In particular, we actually know, or we can estimate, predict, that the Canadian population is growing exponentially. That's about a 1% growth rate per year. The question is whether our previous population estimate from a linear function is going to be above or below what the actual population will be in 2 years. So just think about that for a second or two, and then we'll come back to it. Okay. The easiest way to answer this actually is with the sketch in the first place. We'll go back and answer it in a moment. But imagine what we just calculated. We have 33 million, so we'll have a little break in our scale here. And we just forecasted that after 2 years, well, after 1 year, it's going to go to up to, let's say, 33,300,000, and then 33,600,000. So this is time in years and population. So we used a forecast that was based on this point and those slopes. There we go. But we were told that the population is actually growing exponentially. So we have the same slope initially, but an exponential curve is going to pull upwards with increasing slope, as the people who come in also have their own kids and produce more immigration as well. We're going to get more and faster growth, or a higher rate of growth. And so here's our linear estimate This point here would be the actual population, roughly speaking. And our linear estimate following a straight line is always going to be below this exponential curve because the exponential curve is bending up and away. And so that means our linear estimate is going to be an underestimate of the real population 2 years from now. Okay, so these are classic types of problems that are asked with linearization. Not only what is the prediction, going back one page, not only building the model and then calculating some predictive values, but then asking how closely does that prediction relate, or in what direction does that prediction relate back to what the real function underlying it all is. In this case here, a linear function would produce an underestimate. All right, here's a more classic math type problem. Find the equations of all the lines through the origin that are also tangent to the parabola. So here we've got tangent to, we're thinking linear approximations or tangent lines are going to come into play here. All right, let's sketch out what this might mean or look like. Imagine a parabola over here somewhere, like so. We've been asked to find the equations of all the lines through the origin. So there's lots of lines through the origin. But some of them, this line through the origin would just go like this and would cross this line here. But some other lines through the origin are going to just barely touch the parabola and just barely touch the parabola. So some points on the parabola are going to lead to tangent lines that go back to the origin. Okay, this is a bit more exotic. Let's take a look and see how we can analyze this. The first thing to do is start with the equation of our parabola. Notice it's not a really nicely formed or factored or completed the square form, so we don't know quite what this looks like yet, but it's going to be opening upwards for sure. So this is probably not an unreasonable way to think about the scenario. The next thing we're going to need is the equation of tangent lines. So thinking of it now from the parabola side, we can build tangent lines at different points, and some of them will go through the origin. But let's just pick a representative point, let's call it A, and find the tangent line there. Okay, so if we find the tangent line at x equals A, let's call that L of x. That line will be created using exactly the formula we've seen before for linear approximations, plus f of a. Take the derivative times x minus a plus f of a. And notice that's our variable. So the line, let's say this red line here, it's a function of x, and the a is where we start drawing it based on the parabola. But x is the input, a is a point on the parabola. Technically an x point there. Okay, well, to fill this in, what do we need? We're going to need f prime. We don't have that yet, but fortunately we have f, which is equal to x squared minus 2x plus 4. So f prime is going to equal 2x minus 2. And that means that our linear function will be f prime at a, 2a minus 2, times x minus a, plus f of a, which would be a squared minus 2a plus 4. Okay, so now we have, for any point a that we pick, we have a straight line. Notice the only component of x here is a linear term plus a lot of constants a. So you have to keep your eyes clear about what's changing. It'll be x, and what we get to pick, which is a. We're going to move this to the next page and see how it can help us find the a values that lead to an intersection with the origin. From our linear function here, again linear in x, we can imagine that our point A will lead to a line that goes through the origin if L of 0 is going to equal 0. And that's our x, and that's our y value, or L of x value. So we're interested in the A values that if we pick them will lead to a line that goes through the origin. How do we know a line goes through the origin? Well, if the line gives us a 0y value when we plug in x equals 0. So we can actually set this up, plugging in for x and y. We'll do this in color. So we're saying L of x, or the y value, is 0. That's the interesting point for us when x is 0. Okay. And now you notice we have an equation just in A. And that makes sense. We've said, let's put a constraint on A so that our line that we get when we choose A can only go through the origin. Well, then only some A values are going to lead that to working. And so we can solve now for what those values, those specific values of A will be. So here we're going to have minus 2a squared plus 2a plus a squared minus 2a plus 4. And that's minus a squared, these cancel, plus 4. And that gives us a squared equals 4, or a equals plus or minus 2. Ah! Now remember how we defined this. A was the point on the graph, particularly the x-coordinate, for the linear approximation. And we just found that if a is equal to 2 or negative 2, our straight line approximation will go through the origin. So tangent lines to y equals x squared minus 2x plus 4 at the points x equals 2 and x equals negative 2 will pass through the origin. All right. Now let's just see that and sketch that out on the next page. If we write out our function and evaluate it at a number of points, we can do a quick sketch of the parabola. And the points we get are 3, 4 and 4, and then 7 and 7, and then 12 and 12 on the other side as well. So we have a parabola like this. And from that parabola, we can generate tangent lines. Now let's try this. Let's try this one first. It's a bit clearer. There we go. And here I'll tweak my sketch, which apparently wasn't that accurate. There we go. There we are. At these 2 points, at x equals 2 and x equals negative 2, we get tangent lines that go perfectly through the origin. Any further along, and the tangent lines would miss the origin. Any closer in, and the tangent lines would miss the origin as well. So we have correctly solved for the 2 points on this graph where the tangent lines will contact the origin.